everyone. We are going to talk about clustering methods today as part of unsupervised learning. This is part one of clustering. We will have one more lecture on hierarchical clustering. Today we'll focus on k-means clustering. So one of the students sent me this really nice diagram that shows the machine learning process. At this point, this diagram should be very familiar to you. When we get a data set, the first thing we do is splitting it into training and testing data set, and then we use the training data set to build our training model, which we call a learner. And then using a learner that I've learned from the training data set, then we can use that to build a model after we run the test set. Once we have our best model, we can use it to make a prediction. And once we have predictions, then we can measure our prediction performance, right? So do I make a good prediction, a bad prediction? Depending on whether I did regression or classification, I can either do a confusion matrix performance measure or MSE. So this is all very clear. We've been doing this every week with one caveat, right? This is really the process of supervised learning. With unsupervised learning, the process is a little different, right? So because with unsupervised learning, we don't really have correct labels, we can't really test because we don't have correct answers. Like given a quiz that doesn't have a key or given an exam that doesn't have a key, I can't really measure if you did well on a test or not if I don't have a key. So if you don't have the Y column that gives you the correct labels, which is the key, then I can't really do the testing. And because I can't really do the testing, I can't really measure my performance. I don't have correct answers, so I can't really tell you how well you did on the quiz or exam. I have no benchmark, no correct answer to compare performance to. So in this way, hopefully you'll be able to see that unsupervised learning is quite distinct from supervised learning. So to recap, how do I know if I need supervised or unsupervised learning? It all depends on whether your past data has correct labels or not, right? So if your past data, the existing data set that's given to you comes with correct labels, then you would need supervised learning. If not, you would need unsupervised learning. So supervised learning, to recap, is to use past data, such as customer behavior, to predict the future, such as given a new customer, what is this customer going to do? Okay, we've seen a bunch of supervised learning methods. These algorithms should be pretty familiar to you. And they all follow this trend, test, predict procedure. Unsupervised learning, on the other hand, is using past data to identify segments or clusters. And then the clusters can help us kind of predict where the customer will belong based on the similarity, right? So if your new customer is similar to this cluster, then the customer is probably going to be giving similar behavior to the behaviors from past customer in that cluster, although we don't really truly know, right? Because we don't have correct labels. We've talked about PCA. Today we'll focus on k-means clustering, and then next lecture we'll focus on hierarchical clustering. So when you are given a data set like this, 9 data points, you will naturally see clusters, right? So you probably see 3 groupings. However, the computer does not have eyes, so the computer can't really see this, right? So the computer will need a mathematical approach to compute the clusters with the algorithm. So we can see these, right? And then given a new customer, if we say, well, the new customer is closer to the orange cluster, then this new customer is probably going to behave similarly, right? So that's how we can make recommendations or predictions. So as an unsupervised learning method, clustering requires no Y labels. The goal is to discover structure or groupings in data. So some practical applications include discovering similar products. Say if you are Amazon, you might want to do that. If you're Netflix, you might want to identify similar reviews of the movies. If you're an accountant, you might want to group similar transactions without having to manually categorize each transaction. Maybe we can ask the computer to just identify similarities and file them automatically. You can also, as a marketer, find distinct market segmentation using clustering. So lots and lots of very useful applications in business. The idea is to divide data into non-overlapping clusters. So that's very important to remember, that the clusters should be non-overlapping. When you have data that overlap, then this method can be a little problematic. We find the centroid, the center of the cluster. That's the mean of all the X features. Okay, so if you have multiple X features, then each X feature will get a mean, and the vector of the means will become the centroid. The algorithm seeks to minimize distances of cluster centroids to data. So what we want to do is we want the clusters to be as tight as possible. So you want very little variation within the clusters, and you want big variations across clusters so you can distinguish them. Just as a tip, we'll come back to the code later, but once you build a model in R, then you can easily ask for total within cluster variation with this parameter tot within SS. So tot is not theta tot, instead it stands for total. So the total amount of within sum of squares. So variation is just sum of squares. This is actually very similar to what we did with regression. And we also want to maximize between cluster variation, and that parameter is also readily available with between SS parameter. So k-means clustering with a k of 1 example. So k means the number of clusters. Okay, so if we have this data set with 8 data points along a single X feature, so this is a very simple example, what we can do is we can say how many clusters we want. If I ask for only 1 cluster, then everything will be in a single cluster. So within the cluster, we want to find the center. Okay, the center is really just the mean of all the data points. So this is called cluster. We only ask for cluster. 1 cluster, so this is cluster 1 is the only cluster we're going to have, which includes everybody. Okay, so what we want to do is we want to minimize the distances between the centroid to the data. So this cluster is what you both call C1. So C1 to CK are the different clusters. Here we have a K equal 1, so we only have 1 cluster. And the star, the yellow star, indicates the center or the centroid of this cluster. And what we do is we want to measure the distance between the center to each data point. So the blue lines tell you how far away each of the data values is from the center. So all these distances, okay, need to be minimized. So what we do is we measure the amount of distances for each one of them. We square them. Remember, we always square these things. So they're all positive. We can add them up. So the center is really the mean, right? So the mean of X for cluster K. So this is the mathematical notation for it. And each of the smiley faces is the data point. So that's an X1. So if we want a centroid, which is the mean to the data, which is X of I, then the distance between the two is really just, we take the data point minus the mean. And then we square them, add them up, and that is the amount that we're trying to minimize. Okay, so that's actually what we mean by tot within SS. It's really just the total amount of distances. Now, once we have 2, we can specify 2 clusters. So k-means clustering, the key is that you have to ask for the number of clusters ahead of time, and then the algorithm will generate these clusters for you. So when you have 2 clusters, so each one of them will have a center. So we have C1 and C2. And then we can measure the amount of variation within each cluster. Okay, so these are all the distances. We can add them up. And that will become our total within SS. So it's actually the variations from each each one of these clusters, and we can add them up, and that becomes my total amount of within sum of squares, within cluster sum of squares for this model. Okay, so we can compute the total amount of within SS. The more clusters you have, the smaller this amount will be. When you only have k equal 1, that's the maximum amount of sum of squares you can get. So the more cluster you have, this number will get reduced. The question is, you don't want to have cluster that's too small, because once you have too many clusters, like you have 8 data points here, if you have 8 clusters, then each cluster will have 0 variation, and the total amount will be 0. So eventually, you can only have up to 8 clusters when you have 8 data points, but it's pointless to have 8 clusters for 8 data points, a cluster for every data point. Really, the model really is overfit. It doesn't predict anything. Okay, so what you want to do is you want to minimize the distance of cluster centroids to data. And how do you do that, right? So what you want to do is you want to compute the total amount of variation for k equal 1, k equal 2, k equal 3, and you compare them, right? And then you ask the question which k produced the smallest amount of sum of square deviations. And again, that's this measure. Okay. The computer cannot eyeball where the centroids are, so we need to search for the best centroids using an algorithm. Okay, so what we do is there's a series of steps that we have to follow, well, the algorithm follows. The algorithm will need the user to specify the value of k. So you have to say, I want 2 clusters, I want 3, and so on and so forth, right? But each model has a fixed number of clusters. Then once you have chosen the number of clusters, the computer randomly assign a number from 1 to k to each the point. So this is the assignment. So we'll pick 4 of these to be k1, which means that they're assigned to cluster 1. And then the other ones are assigned to cluster 2 because we only asked for 2 clusters, so now all the points are assigned. But this is a random assignment, so we have no idea how good or how bad these clusters are. This is just a way to jumpstart the process. And then what we do is we measure for each cluster, we compute the centroid, the mean. Okay, so we take these 4 numbers, we take the mean of that, and that becomes the centroid for cluster 1. And then we take all the data points from cluster 2, we calculate the mean, and that becomes the cluster 2. And then we assign each number to the closest centroid. So this is when we reshuffle. So once we have the means of the centroid, then I can recalculate the distance between each number to the centroid. And if say the first number is currently assigned to cluster 1, but if it turned out that it's closer to cluster 2, then I'll get reassigned to cluster 2. So reshuffling will happen during the step. And then we iterate, right? So we iterate, we try to do the same computation, and we reshuffle again. We iterate until the cluster assignments stop changing. When you have a 2-dimensional space, when you have 2 x features, x1 and x2, you will do the same thing. You will, when you have k equal 2, you will randomly find 2 centroids, and then you will measure the Euclidean distance of each data point from these, and then you will reshuffle until you find the best centroids. When you have k of 3, you might have these 3 centroids that are optimized, and then you can measure the Euclidean distance of each data point to the center. The clustering algorithm finds a local minimum. It's not a global minimum, so the solution may not be optimal across the board, but it's a pretty good solution when clusters no longer change. The results depend on the initial random assignment of clusters. So when you change how the random number generator works, then the results will differ a little bit. So what we need to do is run the algorithm a few times and select the best solution. So you can specify how many times you want to run the algorithm using the n star parameter in the k-means command. So we usually run 20 times. You can run 25 times, 50 times, however you want. And then what happens with the k-means algorithm is that this command in R will automatically select the best solution after 20 times, and it only gives you the best solution in the results. Okay, the best solution is the one with the smallest sum of squared deviations. So this is the output. When you specify k-means and you provide the data frame, you can ask for centers equal 3. So that's your number for k. So you're asking for 3 clusters, and then you're asking to run the same routine 20 times. So random assignments 20 times. So you will see the cluster means, right, in the results for the first cluster, right? So we have, and the second cluster. So you can say the clusters, we have 3 clusters of size 17, 20, 23, 17 data points are in first cluster. So that's the first row, and 23 data points in the second cluster. So that's the second row, and 10 data points are in the third cluster. So that's the third row. We have 2 different means. The columns are means, because we have x1 and x2, there are 2 x features. So each one of them has a mean. The mean vector becomes the cluster. Okay, so below that, you can see the clustering vector. It shows you exactly each one of these data values. We have a total of 40 of them. So what cluster they belong to. So it's actually a total of 50, I'm sorry. So a total of 50. So you can see data point 1 belongs to cluster 1, data point 2 belongs to cluster 3, and then you can see the one that I highlighted is the data point number 10. This one belongs to cluster 3, right? And then the output also tells you the within cluster sum of squares, right? So we want to minimize within sum of squares. So these are the sum of squares for each of the clusters. There are 3 clusters, so we give 3 values. And then you can calculate the between sum of squares. So between sum of squares is really just a total minus the total of within, right? So you can see the between is what we want to maximize. So the between cluster sum of squares divided by the total amount of sum of squares is almost 80%, and this is a number we want to maximize. So 80% is actually pretty good. You can also plot the clusters. So we plotted the x values, the 2 x values using the x data set. So you can see the data are somewhat standardized, mean around 0, close to 0 on either dimension. And you can see the 3 different clusters. So the color is actually produced by COL. The parameter COL stands for color. And we're actually using the cluster value to do the coloring. So we actually just take cluster plus 1. Okay, so 2. Color number 2, color number 3, and color number 4 are the 3 colors that we see on the chart. So we can also try different k values to see which one provides the smallest sum of square deviations. Again, this is the total within SS that we try to find the smallest for. So what we do is we can actually use the Opal Plot method to find the best k. So this is actually very similar to the scree plot that we saw in PCA, or principal component analysis, that we are looking at the drops, the dropping of performance, and we want to find the Opal where the performance starts to decrease, or the performance change starts to decrease. So let's say that we want to try k equal 1 to 15. Maximum is 15. We want to go through 15 of these iterations, right? 15 different models, and see which k gives us the best performance. What I want to do is, I want to set up an array or a vector called total within this. I create a vector with 15 spots, and they'll have the value of 0. So I repeat 0 15 times and put it into this vector. And then what I do is I use a for loop to go through all 15 possibilities, right? So I'd run the k-means model 15 times, and each time with a different k value. So k ranges from 1 to k max, which is 15. Okay. And I ask for total within SS, and that value gets stored into total within this, that vector. And so after that, I will have a vector of 15 values, and each of these values is the total within sum square for each of the models. And then I can just plot it. So this is a plot of the within cluster sum of squares, and you can see that it decreases over time because the more clusters we have, the smaller the number is. However, you do get diminishing returns after a while, and also once you have too many clusters, it's sort of silly. So you want to stop at some points. So what we usually do is we try to look at the elbow region where the drop starts to sort of slow down. We want to pick one of these Ks to be the best K and use it. Okay, again, there's no correct solution. There's no best answer. You will kind of just pick what cluster makes sense to you. You might want to visualize and just eyeball and pick that. So the decision is relatively subjective, and it depends on the task at hand, which is very, very different from supervised learning, where we usually have a correct answer or the best model. Some important notes about clustering. The clusters are non-overlapping. The algorithm is problematic when clusters overlap, so you want to pay attention to that and visualize your data, take a look. And if you see a lot of overlap, you might want to rethink whether this algorithm is appropriate. The clusters are not always robust, meaning that when the data changes a little bit, the clusters like completely reshuffle or the centers move a lot. So that's not very good. But that's basically the nature of the beast for this algorithm. It's very sensitive to outliers, especially when outliers are forced into all clusters, and when clusters are forced to be non-overlapping. So there's some newer sort of improvements to the algorithm that requires softer margins, boundaries, in a way that's very similar to the soft margins of support vector classifiers that you allow. You have a way to tolerate outliers. They're not necessarily have to be forced into clusters, and you allow some overlapping boundaries, and that seems to make the clusters a little bit more robust. But using the base form that we have, you have to just keep in mind that when you remove just a couple of cluster outliers, change the data set a little bit, or you use only 20% or 30% of the data, you may get very, very different clusters, right? So when you use different data sets of when you do like a subsetting, then you may get very different clusters, and you might want to question the robustness or reliability of these clusters. So what you want to do is you want to just run the model a few different ways, a few different times to make sure that it's robust, right? So don't settle on the clusters until you're absolutely sure that they work with big data, small data. No matter what you do, the clusters remain the same. Then you know you have a set of robust clusters. Because the calculations are all very dependent on Euclidean distances, you should always center and scale your data. Otherwise, your clusters will be influenced heavily by unit of analysis of your measurements. Again, reminder, there's no correct solution. So it's sort of an art and science. As an analyst, you have to look at your clusters and decide if you're happy with them. Try different settings, different subsets. These are what we call robustness checks. Just run the models in many different ways to make sure the clusters always remain the same before you make a decision about the clusters. And that is all. Thank you very much.